learning outcome 30 then. So free fall describes the motion of an object when the only force acting on it is its weight. Oops. Okay, so that's the definition. And then if we look at the equations of that, so if we apply Newton's laws to it, then if the only force acting is weight, this means the weight is the unbalanced force. Okay, so Fun is equal to W in this case. But we also know from Newton's second law that Fun is ma, and we know for our definition of weight that weight is mg. And then if we divide both sides by m, it cancels out on both sides, and you're left with A equals g. So this tells us that in true free fall, i.e. when there's no air resistance, every object will accelerate downwards at 9.8 meters per second squared. Every object, no matter its mass, accelerate downwards at 9.8 meters per second squared on Earth. Now obviously if you're on a different planet, the same rules would apply, but you'd have different values of g. So on the Moon everything accelerates downwards at 1.6 meters per second squared. On Jupiter everything accelerates downwards at 24.6. And I'll just put a quick reminder, NB, this assumes no air resistance. Which is why it kind of contradicts our everyday experience that you know, if you drop, well, we did it with a piece of paper and a pen. Right, the pen fell quicker than the paper. But that's what we mean by free fall. We're assuming there's no air resistance. Okay, so terminal velocity is the kind of second half of this learning outcome. So when we consider the effect of air resistance, so we're now putting the air resistance back in. And we'll describe it from the point of view of the kind of parachutist, but like I say, it can be equally applied to things like cars. We find that when an object is first dropped, its weight provides an unbalanced force. Making it accelerate. Right, and I'll put in brackets here because usually you're asked this in the context of Newton's laws. Oops, missed out. Okay, so we're using Newton's second law to explain there that there's an unbalanced force and it's going to accelerate. But one of the property of all kind of frictional type forces, so including air resistance, as it gets faster, the air resistance increases. And it will increase until it balances the weight. So at this point, forces are balanced. And the object will move with a steady speed. In a straight line by Newton's first law. Remember, Newton's second law covers unbalanced forces. Newton's first law covers balanced forces. And then last wee bit, this steady speed is called its terminal velocity. And what we saw in the demonstration with the ball bearings is that they have different terminal velocities because they experience a different kind of ratio of air resistance compared to weight. Right? So the smaller one, right, the air resistance is more significant compared to its weight, so it gets a terminal velocity, a lower terminal velocity, whereas a larger one gets a higher terminal velocity.